Today's lesson is 7-3 out of our textbook. It is talking about logarithmic functions as inverses. This is a really important part of what I want you to remember. We've talked about inverses earlier in the year, or all throughout the year. An inverse function is one that undoes another function. We have addition and subtraction. Those are inverses. They undo each other. Multiplication and division undo each other. We have square and square root. They undo each other. And how did we ever find those when we were looking to find the inverse of a function? Is that we switched the x and the y variables. That doesn't look like it. I'll try that one more time. Okay, so we switched x and y. For example, okay, so keep in mind what we've been talking about the last 2 days are exponential functions. Y equals 3 to the x. Well, if I want to find the inverse of that, then I'm going to switch my x and y, and that's going to give me x equals 3 to the y. And you look at that, and we have this problem. We got to know how to solve that equation for y. Because when you're talking about a function, we get y by itself. So how do we solve that? Then we created, not we, somebody else created the logarithmic function to get this in a form that we can write it. And it looks like this. So it is the log base b of x equals y. Y equals the log base b of x. This is the definition. And that is it, if and only if b to the y equals x. So it's just like what I wrote for you up here. Instead of 3, I wrote b. Now, let me point some things out to you that are very, very important that you're going to remember. And you might want to listen to the first few minutes of this video multiple times, because you're going to get confused about things, and it'll help keep things straight. Okay, you have a log and you have the exponent. All right, a logarithmic function undoes an exponential function. They are inverses of each other. But notice in these two forms, whatever the base is here is the same thing as the base there. And up here, when we were trying to figure out how to solve it, how do I solve for y? Well, y is just the exponent on this thing. Okay, so when you see it, y right here is the exponent. So what is the log? The log is the exponent. If I'm looking for the log of the function, like, what is the exponent? And you're going to hear me say this over and over again, so just keep that in mind. And let's go talk about the graph, and we're going to do some graphing and do some evaluating and just simple rewriting right now. So first off, just like we had before with our exponential function, okay, our base, the base of our log will always be positive, okay? And it's going to be, if it is larger than 1, then we will, actually, and before I go there, let's talk about this before we graph. So as I said, the log and the exponent are inverses. And how do we find that? Is we switched the x and y coordinates. So on our exponential, our key points were -1, 0, and 1, and b, 1, and 1 over b. Well, now I'm just going to switch those, and my -1, 0, and 1 will be on this side, and my b, 1, and 1 over b will be here, because that's how we found it. We found it by just switching the x and y values. Okay, so those are my key points, and when I plot them, when I plot 1, 0, it's going to be like this, and you will find out that the rest of it is looking like that. All right, our asymptote now is no longer the y-axis, but it is the x-axis in both cases. So this first one here was b being larger than 1, and over here we're going to have b less than 1, but still greater than 0, just like we have with our exponential. Okay, and what's going to happen, the logarithmic is still growing, it's still increasing, just like it is with exponential when b is larger than 1, and over here it will be decreasing, and so it looks like this when you graph it. Okay, and to continue on that same theme, Okay, we're switching the x and the y. So what was the domain of every exponential function? It was negative infinity to positive infinity. So now that is the range of our logarithmic function. And you can see the lowest value is negative infinity. The highest value is positive infinity. Our range before was 0 to infinity. Now that's going to be our domain, 0 to infinity. Okay. Also, I've been telling you that you could write that as y is greater, not y. Hello. X is greater than 0. And this, of course, can be written as all reals. But you're going to be great math students if you can know that interval notation also. Okay? So keeping this in mind, y'all, the domain right here, x has to be greater than 0. You can never take the log of a negative number. Cannot take the log of a negative number. It's not in the domain, so keep that in mind. Intercept. With the exponential function, it was 0, 1. With the log function, it is 1, 0. Our asymptote with exponential was y equals 0, and so now it is x equals 0. Okay? And to continue on that theme, let's go into something different here. Remember, as I said, the log and the exponential functions are inverse functions. Therefore, when you compose them, now what does that mean to compose them? I don't know if y'all remember this, but that's when you do like f of g of x. Okay? And we did this, and when you get, if they are inverses of each other, this was equal to, ooh, candy question. We'll see if anybody asks this, watches this before class, but it's a candy question. When I compose them, what do I get out? Okay? And I hope you answered x. Okay, whenever you compose inverse functions, you get x. That's how we knew whether or not they were inverses. And that's what this says. So the log and the exponential are inverse functions. Therefore, when you compose them, you get what you started with. That's what you start with. You start right here with x. Okay, so that is, now look at this way that you see this when they're composed. One way to compose them is to write, if you have the log on the outside, so the log base b of b to the x. Okay, that's one way of composing them. The other way would be if you started with the exponential and the exponent was a log base b of x. Both of those cases, you get what you started with. What did we start with? Or every time we compose inverse functions, we get that x. Okay, so what I really want you to get from this, and you'll find out if you do this, how it will simplify your working with logs. Okay, when you do this, if this and this are the same, then the answer is right here. That's what happens here. So back over here, when this base and that base are the same, then the odd man out. And this is what one textbook that I enjoyed teaching out of, John Saxon, he calls these problems, what color is a white house? What color is a white house? It's white. The answer is right there in the question. Okay, but before we do some of that evaluating, we're going to make sure you know how to get back and forth between each form. Okay, so we're going to start off. It's asking us what is the logarithmic form of the equation. Okay, if I'm looking for the logarithmic form, okay, then I'm going to have log in my answer. Now, the key that I keep telling you is the base is always the same, and we've just spent the last 2 days talking about what's the base. The base right here is 6, so that means the base is right there. Okay, the log is the exponent. So what is the log equal to? The exponent. Well, what's the exponent? 2. And that leaves the last number that's left in the problem to go right here. And now, let me tell you something else about this. When you're doing these problems, okay, some people like to think of this as a kick out, but you can check yourself by starting down here at the bottom. And 6 to the second is equal to 36, which is what that says right there. So that's how you know that you've done that problem correctly. All right, let's do another one. And you know what? If you feel like you got it, go do those, pause it, go do the next ones, and then come back and check those. Okay? So I have 8 over 27 equals 2 over 3. I'm trying to write the logarithmic form again. So I'm going to have log. Actually, I'm going to go ahead and box that. I didn't really get my box around that whole thing. My bad. Okay, so I have a log. Whatever the base is here is going to be the base over here. Whatever is the exponent, that's what the log is the exponent. And that leaves the last number to be here. And again, you can check it. 2/3 to the third is 8 over 27. So keep in mind, when you're doing these problems, y'all, there's no calculating. You don't need a calculator for any of this. It's just rearranging the numbers in the problem with the word log. Okay, one last time. Log. Oh, you've got to be kidding. Sorry about that. Log. I got my log. My base is 3. My exponent, which is over here by itself, is 0. And that leaves that to be. So 3 raised to the 0 equals 1, which is what that says right there. So we're good. All right, so the next thing we're going to work on is what is the value of each logarithm. Okay? Now, there are 2 different ways to do this problem. And I'm going to tell you, actually, let me go do this. I will tell you that whenever I do it one way, there's a short way, what I call a short way and a long way. That's kind of, there we go. A short way and a long way to do these problems. I'm going to do it the long way first. And if you want to do it that way, you can do it that way. And then I'm going to do it the short way. Because there are a lot of people, when I only do the long way, they go, why didn't you show us the short way? You have to do the same thing in both of them. Let me just do one and you'll see. So it says, what is the value of the logarithm? I'm looking for an answer right here. Okay, don't know what it is, but I'm going to come over here. The long way is to take this problem, log of 120, a log base 5 of 125, and set that equal to x. And if I set it equal to x, then I'm going to use what we were just doing, and I'm going to write it in exponential form, which means I'm going to take the 5, raise it to the x. 5 to the x equals 125. So instead of writing in log, I'm writing in exponential form. And now I got to figure out how to write 125 as a power of 5. Well, that's where these come back into play. We talked about these back in chapter 6, and I told you they were going to be really, really important next semester. Well, here's where they're coming into play. So you've got to go figure out how to write 125 with a base of 5. Now, you can either know the chart, or you can get your calculator and go 5 times 5 times what? How many times do I have to do that to get to 125? Or you go to the 5s and you find there's 5 squared and there's 5 to the third. So 5 to the x equals 5 to the third. And now when my bases are the same, I can get rid of them, and I know that x equals 3. So what is, but there's no x in this problem, y'all. So I don't want x in the answer. What's the log base 5 of 125? It's 3. Okay, now let me show you the shorter way of doing this problem. I say I have to be able to write 125 with a base of 5. So log base 5, 125. 125 is 5 to the what? That's the same thing you had to do from this step to that step. 125 is 5 to the third. Well, now we are back to this concept right up here that I told you. When you compose them, okay, if I have the bases being the same, then x is my answer. So there's my white house. What color is the white house? 3. There's my answer right there. So you can do it the long way. You can do it the short way. Okay? All right, I'm going to go do another one. So we have log base 4 of 32. So I'm going to say log base 4. I'm going to put my answer like this. Log base 4 of 32 equals x. So we do the little kick out. 4, starting there. 4 to the x equals 32. 4 to the x equals 32. And now, if you go back to your little chart here, you're going, oh dear, I can't, 32 is not in that list for powers of 4. But if you go to powers of 2, that's why knowing these numbers are so important. You can see that 32 is in your list and 4, and they are both powers of 2. So 4 is 2 squared, and 32 is 2 to the 5th. So that means that 4, as we just said, is 2 squared to the x. 32 is 2 to the 5th. So when you raise a power to a power, this becomes 2 to the 2x. You multiply those two, equals 2 to the 5th. I got the same base, so 2x equals 5. Divide both sides. Stop that. Divide both sides by 2. And x equals 5 halves. And so my answer is 5 halves. Whew, that's a lot of work. Okay, well, let me show you the other way. So if I do it my way, that I like so much better, okay, I look forward in 32, and 32 is not a power of 4. But I do know that 32 and 4 are both powers of 2. Again, same thing you have to do over here. You're just doing it when you look at it right here. So that means that 4 is 2 squared, and 32 is 2 to the 5th. Well, in case you can't see, your answer is right here. It's this number over that number, 5 over 2. And you go, well, wait, we didn't do that before, but technically speaking, we did do that. If you take this, well, I'll go ahead and do it. What is the exponent on this number right here? It's a 1, and 3 over 1 is 3. So you don't really have to worry about it if it's the same number. But if you had to rewrite both of them, then it's the exponents all over each other. It is the same thing. Okay? So long way, short way. You may take your pick. I would really, really encourage you to do the short way, because when you get into later on when we have to condense things, you're going to look at this and you're not going to know, or look at this one and not know it's 3 unless you go and do that. And you've got to be able to recognize that in certain problems. Okay, let's go do this last one here. So I'll do it the long way just in case people want it. So I got, I put my answer right there. So I have the log of 64 of 1 over 32 equals x. So starting at the bottom, I'm doing my little kick out. So 64 to the x equals 1 over 32. Okay, and if you have to, go back to your chart. And so hopefully you know both of these. I can't write 32 as a power of 64 or 64 as a power of 32. However, they are both in this list right here as powers of 2. So 64 is 2 to the 6th. 32 is 2 to the 5th. So 64 was 2 to the 6th. And 32 is 2 to the 5th. But I hope you realize that doesn't say 32. It's 1 over 32, which is why it's negative 5. And so 2 to the 6x equals 2 to the negative 5th. And, well, I'll write that. 2 to the 6x equals 2 to the negative 5. Oh, stop it. And the 2's are the same base. 6x equals negative 5. And x equals negative 5 over 6. So what goes here is negative 5 over 6. And I know you don't mind if I go ahead and do it the short way. So the short way would be the log 64 is 2 to the 6th. 32, well 32, oops, my bad. 32 is 2 to the 5th, but it's not 32, it's 1 over 32, so I have a negative. And from here, I just take my exponents because the log is the exponent, and that's negative 5 over 6. Okay, turn your papers over. Now, if no base is written, it is very important for you to remember that it is understood to be a base of 10, which is called your common logarithm or common log. So just like everything else, an exponent that you don't see is a 1. What else do we have? We have a square root, a radical that has no number in front of it. We know that the index is a 2. So with a log, if you do not see a number down here, you need to remember that it's 10. One way that might help you do that is to remember, if you know, that we work in a base 10 numerical system, number system is base 10. Okay, so what is the graph of the log base 4 of x? Describe the domain, range, intercept, and asymptotes. And you need to be able to do this on any exponential or logarithmic function. Okay, so more importantly, and what we've always talked about, the first thing you always want to do is know what your base is. And of course, our base is 4. And so, as we have talked about, that means that our key points are... Now remember, we've been doing negative 1, 0, 1 down here, but we're on the log function. So the negative 1, 0, and 1 are over here because they're inverses. And then I have 4, 1, and 1 over 4. And my asymptote is no longer y equals 0, but it's x equals 0. Okay? Those are our key points, so I'm going to go plot those real quick. Let's see. There's my asymptote. I think this is 0 right there. Okay, and let's go plot those. So at 1, I have 4. Nope, silly me. At 4, I have 1. At 1, I have 0. And at 1/4, I have negative 1. Didn't really get close enough, but y'all got the idea. So we're going to approach our asymptote this way and go further that way. So there's my function. Now to describe the domain and the range and the y-intercept and the asymptotes. Okay, domain, as we said, and we're going to go, I'm going to let you put it in like this way. I want you to put it in Canvas. X is greater than 0. Our range is all reals. Our intercept is 1, 0. And our asymptote is x equals 0. Okay, and I've talked to y'all about this before, but the one that's not all reals, okay, when we did the exponential, our range, these two are always tied to each other. Asymptote has an equals, the other one's going to be a greater than or less than. Okay, now with our functions, not much different than what we've been doing before. Okay, that's our parent function that we have that we just learned basically right here, but the changes are the same. A in the front, if it's greater than 1, it's going to stretch it. If it's less than 1, it's going to compress it. If it's negative, it's going to reflect it over the x-axis. Okay? If we have H always describes the horizontal movement. K always describes that vertical movement. And you take the opposite of H and the same as K. And when you write those and put them all together in your equation, it's going to be y equals a times the log base b of x minus h plus k. Now, one more thing I want to tell you about that. It was easy to tell what changes went with the x and the exponential because it was up in the exponent. Well, here, if there's a change to the x, it will be in the parentheses. It has to be in the parentheses. Otherwise, you don't know what you're actually taking the log of. So it's even more defined when you're talking about the logarithmic. All right, so let's go do these last two graphs, and then we'll be done. We have, how does the graph of each parent function compare? So we did these in 7.2, so we're going to go through and do them again. So the first thing you always want to do is establish what your b is, your parent function. So my parent function is y equals the log base 2 of x, which means that my key points, remember, negative 1, 0, 1, and then 2, 1, and 1/2. And my asymptote is x equals 0. And now I'm going to talk about what kind of changes we have. Okay, this 3 I know y'all tell me it goes to the right. If you had to write that on your quiz, you would say translated right 3. Okay, and you would know this goes up, and so you would say translated up 4. Okay, so this is affecting my x, and this is affecting my y. So what am I going to do to each of those? All right, I'm going to, what am I doing to each x value? If I move it to the right, that means I'm adding 3 to each x value. If I'm moving the graph up, what am I doing to each y value? I'm adding 4. So 3 plus 1/2 is 3.5. 3 plus 1 is 4. And 3 plus 2 is 5. So those are my x values. Adding 4 to each of those. -1 plus 4, 0 plus 4, and 1 plus 4. Now my asymptote. My asymptote is x equals. So what did I do to each x value? I added 3. 0 plus 3 is 3. So that is my new asymptote, and that is, of course, where we always start our graphing. So I'm going to make that a little bit skinnier if I can. Let's see if that works out. So I'm going to x equals 3, which I think is right here. Okay, that was not right. Try that again. Why did you go away? Is it? No? Okay. All right, let's try that one more time. So x equals 3 is this. There we go. All right, so there's x equals 3. Come graph it. Back there. Okay. And my points are 3.5. So right past 3, I'm going to go to 3. And then at 4, 4. And then at 5, 5. It's a little bit strange there. This is the one that approaches the asymptote. So that's the one that you need to make sure you go down far. Make sure you go along that asymptote. And this one, you're not sure what that next number is. Although that was a really bad connection there. Let me try that again. Okay, so we have something like that. That's good. Okay, so let's go to the last problem. Y equals 5 times log base 2 of x. So again, I'm going to start off writing my parent function. Y equals the log base 2 of x. And so my key points, starting on this side with my -1, 0, 1. B is 2, 1, and 1/2. Okay. And what's going to happen? Oh, wait. Then we're going to write my little asymptote. Now, 2 sometimes is hard to tell, so I just want to tell you, we talked about this on the first day. Each time, what's happening to each of these values is I'm multiplying by 2. So if you wanted to do another one, that would be a 2, because I'm going up by 1s. And this one I'm multiplying by 2, so the next one would be 4. Okay? So it just kind of helps sometimes if you know easily how to get the same kind of thing over here. So that's how you could get another point on there if you wanted to. Okay, so what's happening here? I have a 5 on the outside that affects the y. And how would we write that? If I had to describe it, I would say vertical stretch factor, or it's vertically stretched by a factor of 5. So that means that each of my y values is going to be multiplied by 5. So these are going to stay the same. 1/2, 1, 2, and I'm going to go ahead and plot that 4. And now multiplying each of these by 5. So I have -5. I have 0 times 5 is 5. 1 times 5 is 5. And 2 times 5 is 10. So those are my values. X equals. Did I do anything to my x values? I did not. So my asymptote is actually going to stay the same. I'm going to make it a different color since I'm graphing in green. It is still x equals 0, which is right here on that axis. Okay, and so at 1/2, I'm at -5, which is right here. At 1, I'm at 0. At 2, I'm at 5. And 4, I'm at 10. So you can kind of hopefully see this is a definite vertical stretch factor. really stretched it out. And there's our graph. So I hope you found logs to be as much fun as I did. Please come see me or email me if you have any questions. Thank you so much.